Ladies and gentlemen, I'm Jacob Huang, the Executive Director of Hong Kong IS. Welcome to our Hong Kong IS Distinguished Lecture Series on Chemistry. Today, this is the first talk in our chemistry series. So we're very honored to invite Professor Alice Ren, right? A lot of people call Alice Jen, but actually Jen should be Ren. In Mandarin, it's 任广瑜教授. In Cantonese, 任广瑜教授. Okay, so Professor Alice Ren is the chair professor in Material Science and Chemistry Department, and also he served as our provost during 2016-2020. He has done a lot of great job. Thank you very much. And before arriving CDU, he served as a Boeing Johnson Chair Professor and Department Head of Material Science Engineering Department at the University of Washington, Seattle. And he was also appointed as the Chief Scientist for the Clean Energy Institute endowed by the Washington State Governor. And he is a very distinguished researcher with more than 950 publication. Okay. Anybody in the audience get more papers than that? And 66,000 citation, 68,000次, 68,000, with a H index 131. And he also co-invented 63 patents and invention disclosures. And his interdisciplinary research covered organic, hybrid functional materials and device for photonics, energy, sensors, and neuromedicine. And for his pioneer contribution in organic, photonics, and electronics, Professor Ren was elected as academician by the European Academy of Science, and also the Washington State Academy of Science. And he is also a fellow in several professional societies, including AAAS, MRS, ACS, PMSE, OSA, SPIE, etc. And he was named as by the Times Higher Education in 2018 as one of the top 10 university researchers in perovskite solar cell research. And in addition, he was recognized by the Thomson Reuters as one of the world's most influential scientists mind of 2015-2016, as well as a highly cited researcher in material science from 2014 till now. So I can go on and on, many more, but everybody know Alice. So today, he is going to give a very important talk, Printable Solar Cell for the Transformative, Clean Energy, and Sustainable Society. So let's give a warm applause to Professor Alice Ren.
Thank you very much, Jacob, for the very lengthy, wonderful introduction. So it's for a while, I haven't really had any real audience, okay, in front of me to give a talk, right? So this is actually very precious experience. So thank you very much for coming to support this lecture. So, since the title of this lecture is talking about printable solar cell, try to address some of the challenges from the energy part. And then let's start from the beginning, right? Energy actually impact many things in our daily living, right? So, by burning the fossil fuel and produce carbon dioxide, then really create very severe climate changes, okay? So the global warming create a lot of environmental related issue, okay, right? So, and then this also affect clean water and economy and, human health. Especially, this is very critical because right now for COVID-19, the vaccine, okay, need to be stored under the minus 78 degree, okay, then to be delivered to remote area. So if you don't have enough energy for supporting that, even you cannot inject the people with the vaccine, right? So then talking about, the energy also affect global politics and also national security. Okay, so this is quite challenging. But most importantly, the demand for energy now is about 15 terawatt per year right now. It's going to grow to about 30 terawatt, okay, in 2050. And that's almost as a magic timing, okay, because everybody somehow said, they want to have a carbon neutral by 2050, right? So this is some of the challenge we really need to address. So in order to really address energy-related issues, right, we need to include the solution. For example, you need to have a way to generate clean energy instead of burning the fossil fuels, okay? But then, when you create those energy, you need to find somehow, right, a way to store the energy also, because like a solar energy is intermittent, right? Sometimes you have a cloud come in, then suddenly the generation will fall down, okay, right? And then you have day, you have night. At night you don't really have the sunlight, right? So all these things, so you can basically, for example, if you have a good energy storage system, then you can store whatever the extra energy generated, okay, during the daytime. But then during the nighttime, you can get back to supply those energy. But also, Chinese said, 开源节流, right? Okay. Not only you need to have energy generation, you also need to efficiently use energy. So whenever the energy available to you, you don't just waste it, right? But now the last one is also very important. Is a better distribution. All the grids. How do you efficiently distribute the energy? Recently, this happened to Texas, right? During the storm. And suddenly, nobody can have any energy be available because they create their own grids, okay, right? So even, California or other states would like to pump electricity to Texas. They don't have that capability. So, so distribution also very important, okay? So with that said, because I'm limited by the time, I will only focus on talking about how do you have a way to generate efficient clean energy generation, okay? So I just try to also give you an advertisement, right? Next Wednesday, we are going to have a very nice clean, the energy forum, okay, right? And so this is an international forum, and in that, I will actually cover two, topics related to clean energy source and also clean energy, efficient use of your energy. Okay, so since we are living in Hong Kong right now, so it's right next to China. So instead of always use the US as a reference, but then I try to use China as a reference so everybody can understand, right? In order to really try to address the environment, right, issue, right? Then you really need to find a way to balance your energy demands and also your environmental sustainability. So China has 1.44 billion people, right? Consume 6.88 terawatt, right? So I just said, in the beginning, in this year, the whole world energy consumption is 15 terawatt. So China consumes more than 40% of the energy generated worldwide, right? So this corresponding to each person in China, account for 5,300 watt incandescent light bulb burning 24 hours a day, 365 days a year, right? Okay, and this represents 53 of the 100 watt light bulb in that. Okay, so this also translates into, you burn about 1,400 gallons of oil, or about 13,000 pounds of the coal, okay, per person. Okay, doesn't matter you are the infants or the elderly people, right? So this translates to 10.4 billion tons of the carbon dioxide emission, okay? And this accounts for about 29% of all the carbon dioxide emission in the world. So this means each person generates about 7.4 tons of carbon dioxide per year, okay? So then we're talking about what is a possible clean energy source if we don't burn fossil fuel, right? So then you're talking about the availability of the renewable energy and how do you address the carbon neutral demand in 2050, right? So if you look at the availability of the different kind of the renewable energy, talking about solar, wind, biomass, geothermal, and hydro, right? I'm sorry, Punching, I don't put the nuclear in here, right? Okay, but then, if you're talking about, the potential of generate clean energy, right? The sunlight, okay, 1 hour of sunlight is to radiate to the Earth is about 14 kilowatt, okay? And Julie, right? We should talk about per year, whole world consume how many kilowatt? 15 kilowatt. So 1 hour sunshine is equal to all the energy you consume in the whole world, okay? Okay, so that is tremendous. But so if you look at the potential, okay, in here, solar has the biggest potential. But the question is, how do you have enough efficient device to harvest the sunlight to generate electricity out of this, right? So the potential of solar energy, if you're talking about that, instead of talking about 10,000 or the 20,000, we're talking about, we just address maybe 600 kilowatt. That would be good enough, okay? So then start talking about China's renewable energy current situation, right? Okay, China's renewable energy mainly based on hydro, solar, and wind, right? Okay, and then it's also #1 in the world in electricity produced, okay, by renewable energy. And China is really putting a tremendous effort try to create renewable energy right now. So it's accounted for 690 gigawatt, okay? Okay, so 1,000 gigawatt is 1 terawatt, okay? So then renewable energy is already account about 11.5% of the total energy consumed by the whole China, right? So if you look at distributed to hydropower, solar, and wind, right? And the solar is accountable for about 1/3, about slightly more than 30% of the energy consumed. So if we talking about 53 of the 100-watt light bulb, okay, are being consumed, 6 of this light bulb is light up by the renewable energy, and solar is accounted for about 1.8 of those light bulbs. Okay, so this is more or less some of the basic information we want to hold. But then, very encouragingly, China's renewable energy sector is growing faster than both of the fossil and also nuclear power. So, if you just use an example, okay, talking about the worldwide photovoltaic means solar technology deployment, okay, is rapidly growing. If you look at here, 2012, okay, and this is very tiny, okay, almost insignificant of the solar deployment. But right now, the solar in 18, okay, solar technology deployment. In 2018, China has about the capacity of the North America plus Asia, okay, combined in here, right? And it's accelerating even faster. If you look at the rate of accelerating, okay, and by 2030, worldwide PV, okay, is about 1.7 kilowatt, okay. So this is already, we're talking about 15 to 18 kilowatt, so 1.7 is about 10%, right? Okay. In 2020 alone, China added 48 gigawatt and will reach 650 gigawatts. That's a huge number, okay, because if you're talking about their solar deployment. So if you look at this is gigantic, the solar farm, okay, been built in Shanxi Datong, okay, right, okay, and generate 50 megawatt. And if you look at here, in Hong Kong, the installed PV capacity is about 6.3 megawatt, okay? So if you look at here, this is a 50 megawatt, so this is almost can supply this one, okay, can supply for about 9 Hong Kong energy consumption. But then it's a 0.01%, okay, of the Hong Kong. So if we take all the available rooftop, okay, to install a PV panel, okay, then this will only account for about 1% of the energy consumed. It's about 500 megawatt, okay? So then started talking about, what's the potential, right? Because when you start to talk about solar technology, and because altitude difference, so the solar radiation, okay, in the northern part and the southern part, it's very different, okay? Because if you're talking about per meter square, okay, of the area, and then those deep red part can generate about 8.5 to 9 kilowatt per hour per meter per day, okay? Means if I have just take an average about 5 kilowatt per square meter per day of incoming solar energy I can harvest, then assume it's 10% efficiency. Assume I have 60 square meters of the rooftop, okay, and then you can generate 30 kilowatt per hour. This is 30 kilowatt per hour is about the number you power for all your 30度电, okay, to power your whole house utility, okay. So if you counter that, so if I have an area in this hot red area and put a solar farm in here, 120 kilometer solar farm, that electricity generated is going to power the whole China, okay? So this is about the power. When you talking about the scalability, it's become a very big issue, okay? Okay, so then in the whole world, okay, if I have a 5 kilowatt each of this, right? Okay, $6. If I put it one in South America, one in Africa, one in all the different places, that's enough to generate 30 kilowatt, okay, to fulfill the whole need of the mankind, okay, for energy consumption, okay. So, this is all very promising, and I promote like solar technology, but unfortunately, right, to achieve kilowatt scalability, we need to burn more fossil fuel in order to make enough silicon solar cell, okay? Because silicon solar cell is being made from silica, then you take a very high temperature, try to get it all the way from polysilicon ingot, then go to the wafer, then go to the clean room to make solar cell devices. All this consumes tremendous amount of energy. So this talking about energy payback time. It's become very important, right? Because energy payback time is the energy you put in order to make a solar cell. So by putting up a solar cell, then you start to generate energy. But the first maybe 2 or 3 years of the energy you generated, just enough to pay back from the energy you consume, right? So this is really also very challenging number to talk about. Because if you're talking about energy payback time, it's also related to the different area, right? If you go to the north, you have less sunlight, so your energy payback time is much longer, right? Because you have less sunlight to absorb, right? So now, with this issue, right, you're talking about we have to go to dig out more coal to burn energy in order to make solar cell, in order to generate solar energy. That's not good, right? So good news, right, is the new discovery beyond silicon semiconductors, right? Okay, you're talking about organic and also perovskite semiconductors. And when you have these two new generation of the unconventional semiconductors, right? They can be low temperature process with low cost, and they can be made in the flexible form and have a broad application in LED display, FET, lighting, PV, and also integrated photonics, okay? So this is a very broad application beyond some of the silicon things you can talk about. So potentially, you can have $1 billion, $1 trillion industry. I just give you one good example, right? A few years ago, everybody thought, organic semiconductor never going to be commercialized. But now, everybody using OLED, okay? organic light emitting diode, the TV display, your cell phone, everything, are all based on extremely thin, the high definition TV or your monitor, right? So all of that start to, after innovation start to kick in, then continuously you have the things try to make it commercializable. So when you talk about utilize organic semiconductors, they can use for organic solar cell and can be used for perovskite solar cells, right? And you combine, the possibility of the solution printing. Can you imagine, right? You're making the silicon semiconductor, you go to cutting wafer by wafer, then you go to batch by batch, try to make your solar cell, right? And if I can print solar cell, okay, just like I print a newspaper, right? And I just have a machine within this HKIAS, okay, size. I can print in a lot of solar cell out of this, right? So you can, because the efficiency of the perovskite already also have a similar to that of crystalline silicon. Okay, they can be also be used for energy grid application, but also can be used for, because they can be also made for some commercial consumer products, okay, wearable electronics and also building in PV, right? So combining with all these advantages right now, then this is a two family of the semiconductor being widely explored for solar cell. And this is just to show you, right? Some example about perovskite, just in the short period about 10 years, okay? And this can, in efficiency, increase from 3.9%. Now it's 25.5%, almost exactly same like crystalline silicon, okay? And so this is show you, right? Once people invest brand and also try to come out with some innovation, it can continue to have very accelerate development of the technology. But then when I talk about energy payback time, right, okay, then this is show you, okay, if I use a perovskite to make a tandem cell with a silicon, energy payback time is about 13 to 14 months, okay, but then you want to have a brighter, okay, thank you. Okay, then if I go to use a CIGS, CCTS, or perovskite and perovskite, you can see that energy payback time, I talk about silicon, is about 2 to 3 years, right? Okay. Now this is about 1 to 1.7 months, okay? And I put it up for about 2 months. I already recovered all the electricity going to enough to pay back my technology, okay? So then why this has become everybody becomes so vigorously interested in this area? Because, okay, independently, perovskite is a nearly perfect family of semiconductors, right? Okay, they can have a tunable band gap. So simply, they're very simple, right? You have some ammonium salt and just mix with a lead iodide in the solution, and just cast film, print it out. Wow, you can already have a very highly crystalline perovskite form. And by tuning their different kind of ammonium salts, and also there are different metal in the center and the different halide, then you can have vast variation of the different kind of perovskite, okay, to tune their band gap, tune their property, and also tune their not only absorption but also tune their emission, okay. So if you look at in here, depends on the different kind of cation you use, you can make it 3D, 2D, 1D, all kind of the semiconductor out of this, okay. And most importantly, silicon is never be a good emitter, right? You don't make LED out of the silicon. But perovskite is very fluorescent, okay? So you can have from the blue to all the way to near infrared, okay, of the perovskite based LED, okay? So now you can suddenly use for laser, for solar cell, for laser detector, and also LEDs, okay, for different kind of application, right? So then talking about organic-based semiconductors. So previously in here, one of the things I forgot to explain to this, one of the distinct property of the perovskite is to have the very long carrier lifetime and also fluorescence lifetime. Okay, what does this mean? Because it absorbs light just like a silicon. They automatically they have a very low binding energy, only about 15 or 20 electron volt. Okay, so as a result, they can separate. The photon can separate into the hole and the electron. Okay, right? Okay, but excited electron charge can separate into the hole and electron. Okay, but in here, the binding energy, exciton binding energy, is much bigger, right? It's much less easier to be separate. So organic semiconductor need to have what? You have one is called electron donor, one is an electron acceptor. You have to sort of blend them together, okay? So take advantage of the donor property and the acceptor property. So when you mix them together, shine light on it, then hole will go to the donor, electron go to the acceptor, and charge will be separated that way, okay? So by doing that, compared to perovskite, it's a little bit more complicated because now you have to control their molecular packing and also their morphology. Okay, because if you look at that, this is an aggregate or some acceptor be aggregate together, pack very nicely. Okay, so because all this will have the path, okay, for electron to sort of transport, okay, from that to the cathode to be collected, okay, and hole will be going down to the anode to be collected, okay, in that. So you need to find a way to control the packing, control the morphology, and also control the light absorption, and also control the energy, of those donor acceptor. So when you mix them together, and they can have an easy charge separation. So all of that need to be simultaneously taken into account in order to generate efficient organic solar cell. So so this is compared to perovskite solar cell. Fluorine acceptor, C60 they developed fluorine acceptor, been generated for more than 20 years. Okay, so people put in tremendous effort, and no matter what you do, you get a PC around maybe 11%. Okay, right? And more recently, one of my co-author Xiaowei Zhang, okay, and also start to also promote the non-fluorine acceptor, right? So this means the fluorine and non-fluorine means another fluorine, okay, right? Then you can, based on all the different kinds of molecular design, okay, you can tune their absorption, you can tune their energy level, you can tune their molecular packing, all the different property, okay, in order to make a device out of that. So in less than few years, it's already improved from that to 18%, but already have a potential go to 20%. Okay, so this is incredible. Okay, so during just the past few years. Okay, so I'm not trying to bore you with all kind of this is molecular structures, right? So when I show this to my wife, then my kid, they usually say, "Why do you show us a lot of turtle shell?" Okay, right? Okay, they don't know what does that mean, right? Okay, right? So anyway, so I just used 2 slides to maybe briefly talk about this, and you quickly go over this, right? So in the original design, non-fluorine acceptor, we talking about ADA, acceptor, donor acceptor type of configuration. That's a linear type of thing, is that right? But then in this kind of configuration, and it's relatively difficult to really get a high efficiency out of it because intramolecular charge transfer is quite strong, okay? And then your fluorescence lifetime is very, very short. And that, as a result, you tend to have relatively also large VOC loss in that. Okay, so in that, we sort of take this into account. How do you develop a pseudo 2D type of a molecular structure? Okay, in our JAX paper, talking about not only you have very strong intramolecular charge transfer, but also because you can have those transient dipole moment also by utilizing large, more delocalizable conjugate backbone, okay, and then you can balance that transient dipole, okay. As a result, okay, you can, in those later on I will have an example to show you, right, and the so-called the new development of non-fluorine acceptor called Y6 really get a very high efficiency out of this. And there's the same thing to talking about, previously we said this is sort of pseudo 2D type of, two-dimensional type of acceptor. But then, in this, we have sort of pseudo 2D type of electron donor also, right? So not only you can develop from acceptor point of view, you can also develop from a donor point of view, okay? So in one of this work, by working with Nan Li and also my former postdoc, Gao Ke, right? Then we achieved the highest efficiency in all small molecule devices. So, and this is a work, being pioneered by Zhou Yinping, making this a Y6 material, and then working with our colleague Angus Ip, okay, in here to study the reason why this type of molecule is this non-foreign acceptor is very efficient. And if you can recall, this is exactly similar type of pseudo 2D type of structure, but then instead of ADA, this is ADADA, so some a little bit more sophisticated. Okay, as a result, okay, you can see they can form very nice single crystal out of this, a very relatively large size single crystal. And then when you have this molecule, when they start to crystallize, and then they start to pack, there's a molecular interaction start to pack, and then you can see, the packing of that. So from acceptor, then you pack it from a linear chain, like one-dimensional, then start to form the two-dimensional, and then but then stacking on top of that, then it becomes three-dimensional. And this become very interesting because all the stacking of those acceptors, they form very nice electron transporting channel, okay? And then the overlap of all the core, okay, become the backbone for transport holes, okay? So then, the side chain stuck into this core in here, so they perfectly, without cause steric hindrance to really twist your backbone too much, okay? So this is actually very intelligent sort of molecular design result in a very nice crystal. So this is a molecule. It's very rare in organic semiconductor. It's called n-bipolar transport. Semiconductor not only can transport electron, but also can transport holes. Okay, both charge they can transport in that. So this is quite important. So that resulted into about 15.7% efficiency. More recently, our group, by tuning the heteroatom instead of sulfur, then put in the more polarizable selenium onto this molecule, and then you can see, because the stronger interaction of the selenium interaction, okay, really helped the packing in the tighter space, okay. So your pi stacking and those acceptor interaction. Okay, it really, if you look at their crystal structure, okay, they form tighter packing. As a result, okay, you can go to 17% power conversion efficiency, okay. And I will show you some of the things we learned, okay, because we have a work expert here to do all kinds of molecular simulation and molecular dynamics, okay, but also, how can we learn as a material scientist, learn from the fundamental. Okay, this is some single crystal grow into that. Okay, so I will show you, the molecular modeling of the packing. So you can see this is a linear chain type of molecule. They form like a zigzag, zing, 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 like that. Okay, they pack. Okay, so this is the thing happened through molecular design, happen naturally. It's not because I asked them to do that, right? Okay. So, but then they sort of also stacking for that, and with a pi distance 3.5 angstrom. So, but then for molecular engineer, new molecular engineer, non-foreign acceptor, right? Then you can see that this acceptor, then they have sort of 4 conformal isomers, right? So the first one is you have one unit, and M will be overlap with an MM prime, so you form like a linear, right? So instead of single molecule, now you connect into like a linear line. But then when you have another 2 isomers come in, then they start to stack on top of each other. This one become a 2D type of arrangement. Okay, so you can see that this is a new one in our new design. Okay, then they form almost very order packing, all the acceptor stacking, just right on top of each other. So this will facilitate you to really transport your charges. So if you look at this, is a very beautiful single crystal, and also generated from that. You can see so flat. Okay, all those things sort of line up. Okay, become very beautiful because this stacking in here. It's a flat stacking on top of that will facilitate you to really transport your charge in a more efficient way, right? So if you look at here, compared to the Y6, then the molecules still have some sort of tilting. But in this newly designed system, then you can have a basically very flat type of packing in that. So if you look at the distant packing is a 3.3 angstrom compared to about 3.6 angstrom in your crystal structure. So, but besides that, to design for better transport and also absorption, another way to do is how do you really minimize all the VOC loss in here. I just used one slide to summarize that. This may be several years worth of work in that, right? But then if you look at here, this is amazing, right? We all think gallium arsenide or silicon is already very efficient semiconductors have very low VOC loss, okay? But if you look at here, gallium arsenide, the energy loss is 0.31 volt in here. Right now, okay, in perovskite, we can already, this is our recent result, already get almost exactly the same as the gallium arsenide in the VOC loss, okay? And even in organic semiconductors, 0.49 is also already getting close to that of the regular perovskite, okay? So all this means, if you have a way to molecular engineer your material and find a way to process it in the proper way, you can really significantly reduce that. So this is our result last year. So we demonstrate this NREL means National Renewable Energy Laboratory. This is in Colorado, Boulder, right? Okay, and they certify all the different family of the solar cell, and with the highest efficiency will be put in on those so-called more like Gin's chart, okay, type of thing in that. So I'll put a CTU on the map, okay, first time in the world, okay, right? 7.5%, certified the number in 2020, right? About September, okay. So then recently, if you look at our results coming up, is already getting to 19% and continue to be moving up. We hope, okay, we will have a several result and be disclosed, okay, and then getting close to 20%. So that will be really blow everybody's minds off, because how can you utilize those materials, right? So I will show you, okay, when I said, we can print solar cell like print a newspaper, right? Okay, then you may think I'm joking, right? Okay, this is what exactly show you. So this will show you, go through a different stage, okay, layer by layer. They are printing different kind of material from the whole transporter, print your light absorbing material, even at the end, try to print the silver electrode on top of that, okay? So, you can see, if I can print the solar cell like this speed, right, or continuously, okay, what kind of, how many solar cells can I generate per day, per week, per month, okay, right? And so this is exactly the things we are talking about. See, now they're printing silver ink, okay? So they are printing the electrodes right now. Okay, so with that said, okay, I would like to also use a few minutes to talk about some of our recent discovery, okay? And this is more importantly, okay, because we have a contribution of chemistry Professor Xu Zhentao. Where is Zhentao? There. And also we have, the Zhonglong, right? Where is Zhonglong? Okay, in there, to work together to address one of the most challenging problem in the perovskite solar cell. Okay, because as I said, perovskite solar cell mainly made by lead as a metal, right? Okay, but everybody knows lead is will cause some health issue and also environmental impact in that. So especially the perovskite is water soluble, right? So imagine you make a solar cell in that, and then you mostly put it outside, and then hit by the hail, hit by the rain, hit by all kinds of things, then may break the seal, then rainwater come in, extract it out, and leak into the ground. Okay, so that everybody will be attacking the perovskite solar cell man. I mean, this is not good for human health. So how do you come up with a way to prevent this from happening? So our work, is trying to deal with that. And recently, several very high impact paper also coming out talking about mimic. You make a solar cell out of that, then you try to hit it with a stone, hit it with a sand, hit it with rain. Okay, then you can see once it's water getting in, then your perovskite basically is gone. Okay, so then they try to come up with a way to capture the potentially water soluble lead. Okay, so we did this because one day, the Zhentao come to our lab, say, so I make this powder things, okay, and what can you do with this, right? Okay, so we basically said, okay, we can try to make something out of this. So we try to take advantage of, the so-called meta-organic framework, okay, and this is basically you're talking about some of the organic linkers, right? Okay, and also some of the high valent ions. You sort of find a way to react them together, so they form a 3D type of network. Okay, and this is a 3D network. Usually, they're very older, and people try to explore that for many different other applications. Okay, but this kind of a 3D network, okay, don't really have very good charge transporting property. Okay, so basically it's an insulator. So it's very limited if you want to use that for those solar cell application, right? So Zhentao come up with a design. They take some organic conjugated units, okay, and then design with also many of those SIO group, okay, sort of attached with this linker. So when you react with a carboxylic acid with zirconium, okay, and then they form those very nice 2D type of working, because you have the SIO to provide some of the stereo hindrance, okay, from making the 3D, okay. And one thing very nicely is this SIO, okay, have a lot of functionality use, right? SIO is very easily to react with lead, okay. So lead will react with SIO to trap from lead sulfide, right? Okay, and SIO, when you expose to oxygen, okay, outside the environment, the SIO and SIO will oxide to form disulfide bond, okay. So they also cross-link it, okay, to form very nice network, okay, to prevent maybe water and also prevent outside external stimuli from penetrate into to destroy your perovskite. And SIO also can react with top electrode, right? If I use it on the top as a transporting layer, SIO will react with silver, right, to form HKIAS, that means a silver sulfide bond, okay, silver sulfide bond. So with all this as a potential reaction, then you take advantage of that. You can see we've coated on top of a perovskite and try to expose the perovskite to very humid Hong Kong environment, right? Okay, and with many days, if you don't have this coating, right, then perovskite react with moisture and tend to decompose relatively easily. Okay, so this means you can use that as a protection layer, and then we basically utilize this as also charge extraction layer. Okay, and then this can have very good contact with the top silver electrode. Okay, as a result, you can get a very high efficiency out of this. And most importantly, this is in order for things to be commercial, you always to fulfill so-called telecordia 85-85 test, right? So this is a 85 degrees C, 85% humidity, and you heat it under the sunlight, okay, in the operating condition, okay, for 1,000 hours. This is a so-called accelerated testing. Okay, so this is a very stringent test. It's not just a lab demo. Okay, right? So you can basically still have very nice stability out of this. And then, if you're talking about reason why can we indeed capture lead, so we use TOF SIMS, right? Okay. Time of flight, secondary ion mass spectroscopy, okay, right? This is whatever the full name of that. And you can see that without this morph, right? And then, when you expose to those humid conditions, the perovskite decompose, but then they will start to diffuse out and go all the way to silver electrode. But then once you have that morph, okay, covered layer, then morph basically absorb all the lead, okay, prevents that from penetrating to electrode. So this is also the slide to show you, the absorbing capability, the kinetics, okay, of absorbing lead. How fast it can absorb lead? If you assume I can absorb lead in 2 hours, then it's too late because it all go down to the water. So you need to solve that within the second or minutes or things like that. Then you already absorb most of the your lead. Okay, so this is a very rapid kinetics. Okay, as a result, we also simulate in the acid water by adjusting the pH value to about 5.6 to mimic the acid rain, right? Okay, because rain maybe can be acidic, so you can maybe more reactive to your perovskite, right? So basically, they can trap more than 80% of the lead, okay, in that. So this is Zhentao happily holding to the other solar cell and have a take picture with us. And this when we came out, and this captures the attention of the full international coverage, okay, because from the Europe, from the US, and also from the China, okay, all report in this thing. So now I will try to lead you to dream, okay, about the imagine, okay, this technology. After I show you, with all the printable solar cell technology, and how can you become useful? And remember that, okay. So I maybe give a quiz, right? So all the rooftop, okay, been used by in all the Hong Kong's rooftop been used for solar cell can generate how many megawatt? Maybe only 1% of the electricity, okay, of that, right? But if you look at that, the reason why, because it's just like in real estate, right? Then you buy a house and say location is very important because that's determines the value of your house. But then, for solar cell, you're talking about efficiency, and efficiency, okay, as the determination. If you can make it in the area, same area, twice more efficient, then you only need to occupy smaller area in order to generate same electricity. So this is exactly the things we are talking about. So with the picture like that, right? You have all the very small area to put your solar cell. So it's very tiny, right? Okay. So if you just try to use this regular solar cell, like Sanxi Datong, put in such a big area, right? It's almost impossible. So what shall we do? And then first thing, you can take a perovskite, coat it on the silicon. Okay, you can adjust the band gap to absorb different light. So you make a tandem cell out of that. Suddenly, it becomes your module from usually silicon is about 20-something%. Now it's close to 30%, and the module of this tandem cell is now proved to be 25%. It will be deployed in Germany right now. So it means I can generate 40% more of the electricity in the same area. Okay, so this is the first thing, right? Okay. Then the second thing is how can we turn this small volume into all the skyscraper into the solar farm? Every window, okay, of this of your building can be a solar cell. So we are working with Nambo Jituan and also Mondo Green in this project. Okay, and then if you look at that, they are Nambo Jituan. They have I think the leading supplier of the low E, mean no emissive glasses, right? That reflect all the infrared light, okay, to keep your building cool, right? Okay, so but if I combine the semi-transparent solar cell on this low E glass, right? Then basically, I can absorb most of the, because I have a near-infrared absorbing OPV, right, the solar cell. Then absorb most of infrared light, generate electricity, but then you let the visible light come in, okay? And so you can basically have a very energy conserving and also energy generating building, okay? So this is a big one. And they talk about with more innovation. This is Hong Kong's mountain, right? I think Jacob always go out to have a hiking, right? So then enjoy life. So they can see all the solar cell maybe, generate from that, okay? And then you're talking about, this is Sartan, okay, area, right? They are trying to, talking about building on the highway, the soundproof and with all those cover, right? All of that can be a semi-transparent solar cell, okay, based on that. So you can basically have a solar cell everywhere. Then you're talking about the new generation of the Tesla, right? Okay, and Tesla, one of the things is they all like to have the glass and the roof glass, the window. So all of this can be semi-transparent solar cell. Okay, laminate in that. So with that said, you combine low E glass with semi-transparent solar cell, then you can basically apply that to almost everything in that. So more importantly, okay, I show you print out solar cell continuously. I can make a curtain out of this, right? I don't even need to deal with glass. I said, I make a curtain of this. In every one, I can have a different color of a curtain, different kind of a solar cell. Then you have different color curtain. And then I can make it flexible, right? So everything you wear, you can charge your cell phone. You can, in your wearable electronic, your sensor will be a lot of self-powered sensor out of this, right? So all of this show you, right? With imagination, you can basically come up with many different things. So what does this mean? So this when TVB interviewed me in February, right? Okay, then we're talking about this is a semi-transparent solar cell generated, can potentially change the daily life of everybody, and also can potentially offer, especially Hong Kong, a very good way to deploy solar technology because you are not limited by the tough roof in there, right? So we actually put together a very nice green technology fund, okay, proposal, try to really address this issue. So, in the past 4 years, I served as a provost, right? Okay, so I sort of try to do my research part-time, okay, right? Okay, and because only the time I can do research will be at night or be at the weekend, okay, right? But this is actually one of the most productive time in my career, right? Okay, and we basically published more than 150 papers, okay, but then during this period of time, and then you can see you come up with all the leading material, energy, chemistry, and also nanotechnology related papers out of this, right? Of course, many of our collaborators, like Yunqi, like Zheng Tao, like many Dang Yuan, all contribute into this, right? So then this is not a really self-promoting, but then the reason why I can do that, when I come to Hong Kong, I come by myself, right? But then somehow we nucleate and grow. Okay, so this is like material science, and now it's about 20 people. So Zhonglong, unfortunately, that day you were not here. Okay, but then actually with all this wonderful student and also postdoc, okay, I actually did a much more productive work also here. Okay, so who said student or postdoc studio are not good enough, right? So actually they can, if you have a will, you have a way, okay, to really get something out of this. Okay, so that's it. Okay, thank you very much. Okay, thank you very much for your attention. Yeah.
Thank you, Professor. So we have a Q&A section. We should have a question from the audience and also a question from the Zoom online. And I will start with type the question right here. So I think the first question will be Sir. say for our audience. So, Chen-Yi, yeah.
Come up with a technical question. The first part, you show a lot of organic molecules. The first part, you show a lot of organic molecules. That time, I was thinking you were going to talk about normal electronic structure, blah, blah, blah. But turns out you talk a lot about stacking model of the molecules. So the first question is,
How many questions do you have?
I have a few of them.
Okay.
The first one is that stacking model and electronic structure of the molecules, which one is more important? The second one is if the stacking model is important, like you stack it with the most of them should be pi stacking interaction, and the distance between molecules is over 3 astra, I guess.
Mm.
So the distance is still large, right? So I think, is that sufficient is that good enough for transportation of electrons or holes? Why don't you create some cross links, like covalent cross link, and make it even shorter, even more efficiency for transportation?
Yeah, because, okay, maybe I answer the second question first. Okay, when you're talking about pi stacking, for example, you can get about, say, 3.3, what that we demonstrate. That already considered very, very good, okay? Because for charge transport, because a lot of ordinary pi stacking or those stacking is about 3.6, 3.8. Even you have a graphite, okay? But when you talking about graphite, pi stacking also, right? Okay, then the distance of graphite is also only about 3.3, 3.4, okay?
But if you consider in-plane conductivity and transport conductivity, this will be still.
So this is a thing in that, right? Because depends on different kind of applications. So this also answer your question. Control the stacking also, or the packing is also very important. The packing, if you have flat thing, they all want to what? Pack either this way or this way, right? Okay, because to like a pancake, you stack it up, right? In that. So for solar cell, because the charge you want go vertically, right? Okay. So you want to pack face on your pi stacking, your molecule. You want to control them to pack on face on. But for FET, okay, field effect transistor, right? Okay, and usually in semiconductor industry, you want to line it up because horizontal is the gate of the, and also source and drain gate. So you want to transport in the lateral way, okay? So it depends on your application and depends on your way. You can find a way to control the interaction, because if you look at that, right, then you tune their interaction. For example, pi stacking, right? Okay, large pi ring, and then you have a lot of side chain. Side chain have a van der Waals interaction, right? And then you have a lot of those heteroatom in that, sulfur and sulfur interaction, selenium sulfur interaction, all the different kind of interaction. When you have all those intimate interaction, put that together, then you can really control their packing and also their resulting morphology out of this, okay? And that impact your charge transport, okay? So this is when you're talking about your model is how do you molecular engineer your interactive forces. When you're talking about self-assembly, so the stacking is no different from the self-assembly, okay, right? So when you have all those molecules, how do you really control? I throw those molecules in, they all line it up very nicely. Because, for example, archaeocyle on the go, right? Then cyle anchor on the go, and then archaeo chain of those things, they have van der Waals force, right? Each carbon you increase the number of carbon, then you increase about the interactive forces, okay? 2 kilocalories per mole of the interaction in that. So as a result, after you do it for a while, all the archaeo chain will all stand up, okay, and then tilt in a certain angle to create very ordered assembly, right? So all those interactive forces being explored, and from the original pioneer by George Whitesides, but now people in the field, okay, have all the different kind of tools you can try to tune your material. Okay.
we already have many questions online, including your son, Shang Ren. Say, nice job, Dad. The turtle cell makes sense, right? It's number 4 question. So number 1, from Angus Rocket, outstanding talk. The OP.
Oh,
Angus
Rocket,
Rocket, yeah.
not the Angus here.
Not here. Yeah, the OPV result is really remarkable. One problem for small conjugate molecule is solubility. Could you comment on how you improve the solubility while remaining the property you described for V6 in related materials?
So I think just like what I mentioned to you, when you have a molecule, okay, and you can tune their, for example, those molecules, they have a lot of side chains, right? Okay, those are either side chain. If you have archaeal chain, then archaeal chain tend to pack really nicely, so it's less soluble, okay, and they're very easy to aggregate together. But then if you put a side chain, put a branch out of this, right? Okay, so just like if I put my thing with the arm, then Jacob cannot get close to me, right? Okay, so this side chain will prevent, just like a bumper, okay, prevent people from getting close to each other. And so when you talk about solubility, it's a related solute and solvate, your solvent, right? Try to surround your molecule to make it soluble. So you can actually tune that relatively straightforwardly, okay?
One question from the audience. Mm-hmm. Yes.
Very nice presentation. I have 2 questions. Okay, I think
Wow.
I have 2 questions. The first one is related to packing. I think you showed us a very nice looking packing in a crystalline state. However, I think during the fabrication of the solar cell, people never allow so much of time to settle with the perfect packing. They'll be either doing the solution process or doing the chemical vapor deposition. I do believe the packing will be considerably different from the crystal.
So single crystal is ideal situation, right? But then when you talking about you have to blend with a donor material also, right? Then that will affect your packing. But then, fortunately, okay, those Y6 or this kind of a molecule, they still try to find themselves, okay, to find it. If you look at in that, right, okay, in one of the slide made by talking about OPV one. Okay, in here, right? So that basically, this one is in reality is what you have. You will have some localized area of those molecules can find each other and pack like that. And then but then the question is, how do you tune their ratio? How do you tune their processing conditions? Then they can have a so-called face-on packing. But then most important thing is not the whole thing is crystalline. But then you have to find like an island, okay, for those charge to go around and then to find a way to transport. Okay, so
yeah, I think that's an ideal situation.
This is not ideal.
Yeah,
this is
yeah.
a
But
reality.
can you develop any kind of a physical method to prove it? Okay.
So I think the people, okay, this is already in this field, okay, like the guy from North Carolina State, Alday, right, okay, and also Fendil, okay, all those guys have published many papers in this field talking about you can use soft X-ray or all the different ways to really probe into the length scale, okay, multi-length scale, because they're talking about in a certain region, then you have a different kind of length scale of those aggregate formation, okay, and this has been actually well studied, okay, established in the literature.
Okay, yeah. I think my second question is a rather general one. You talk about the energy payback time for the solar cell. Can you also comment on the energy payback time for the nuclear power plant or the hydroelectronic power plant? Because I think for building this...
let me, hydropower, okay, you limit by your, how many 3-gauge dam can you build, all right, okay? How many rivers do you have, okay? So you limit by you only maybe have a big river, okay, but not every pond, every river you can use that for hydraulic electricity, right? So that limited location is already limited that, right? But nuclear power plant, we will have, the next week you come to, that workshop, okay, right? It's talking about 10 years after Fukushima accident, right? Okay, right? Okay, why people are so concerned about Fukushima accident? Because, even now, after 10 years, you still don't dare to eat the fish, okay, from that region. You don't dare to import the thing from that region, right? So that call, because it's very nice when it's okay, when you are operating that normally. But once something happen, right, okay, do you want our Hong Kong surrounded by 10 different nuclear power plant? Maybe not, right? Okay, so this is already get the case closed, and then you have so many opposition about the nuclear plant, okay, in Taiwan and all the different regions, okay, right now. So it's a debatable political issue, right? But then topics, but then nuclear, okay, if you don't care, have a nuclear plant right next to your door, okay, in your house, right? Then you can basically scale it, right? Because just to put in the nuclear reactor, you put in more dense nuclear reactors in it, right? Then you can have a very efficient electricity, quite clean, right? Okay, and if no accident, right, it's quite clean. Okay, so this is a fundamental issue for you to decide what do you want to have. Okay, but then. For then, I would say, man, if I can have sunlight generate electricity, I would prefer that, right? Okay, so this is just one type of the technology, but of course, this is not for everything, right? You have wind-based technology, right? You have hydraulic-based technology, but it's all clean without burning fossil fuel. That's all we want. You need a collection of all different kinds of things. I'm just propose. One thing today, I'm not saying, solar cell will replace everything. I'm just talking about the printable solar cell will address one of the fundamental issues, scalability. Okay, scalability, because you never can burn enough fossil fuel to build a silicon-based solar cell. Okay, okay. So today, with all this, I'm talking about, you can also give you a lot of innovation. So all the solar cell with silicon is very rich, very, I cannot say it ugly, right? But then, maybe, I can make a red color of the solar cell, and Julie can wear on it, okay, right? Okay, I can power your cell phone, can do the things that, because I can tune it basically any color I would like to have. Okay, tune the band gap, tune the color, make it wearable, make it, every building, not only window. I can make it even experience the exterior， 它的那个外壳啊，你的每一个 building, I can make it in the decoration like a different kind of color. If, for example, I can have ivy leaves, okay, right? Okay, all made by the solar cell.
So we have too many questions. So maybe you can answer 1 minute for each question.
Okay.
Hello, if I would like to find out more about efficiency, weight, power density of your printable solar cell, what could the best place that I should look at, since you have so many paper published from Park Kong Si. So
I think this is our colleague.
Oh, really?
Yeah. Okay. Okay. So if you
want to email to you.
If you want to look into all those information, right? Because each individual paper is published have some certain focus in that, right? So if you have interest, just come to visit my office. We can have a cup of coffee, or we can discuss about this. Okay, I think that I can answer your question.
Yeah. Number 3 question. Number 3. Sorry that I have joined the sharing late. Have you conduct any side trial of the printable P from Bella Wang?
We haven't conducted the side trial, okay? But then, for perovskite solar cell and perovskite, especially perovskite-based silicon tandem, I think Oxford PV, okay, is going to deploy that this year to Germany, okay? And then, Many of the postcard company also in China right now, they get a heavy investment. They are trying to make the postcard solar cell out of this. And I just received this announcement, right? Actually yesterday, right? Talking about postcard solar cell in 2030, going to have a capacity about 130 gigawatt. Okay, okay. So this is will be huge. Okay, for this technology. Okay, so this is a quite serious development. It's not just a lab curiosity. Okay.
Oh, Panchi.
Alex, thank you very much for a very exciting talk. But I'm not going to debate on nuclear power. Okay, I'm going to ask a question about your talk. You mentioned about the encapsulated device, the stability and the lead capturing. But the efficiency is about 22%. Then you still have 78% of the eventually will come out with heat.
Oh, you mean the capture lead, right?
But I'm talking about the stability. Okay.
Stability.
Because if you, with the encapsulation, the temperature can get higher. Okay, of the device can be getting higher, and eventually might damage your molecular package.
Okay, so this is exactly why we do accelerate testing, right? It's heated at 85 degrees C. Okay, so if you have my solar cell put in Hong Kong, if I, for example, right, if Hong Kong have 85 degrees C environment, we already dead. Okay, we already cooked. So that's already go beyond. So I think the Louis is here, right? All the semiconductor device, you do accelerate testing. That's a telecordia concept. Okay, with all the photonics or all the telecom, right? They use standard 85 degrees C, 85% humidity. Okay, and 1,000 hour. Okay, testing. That's in the environment. That's depends on you have a hermetic packaging or different things. So that's the standard.
So you mean there's no problem with the stability?
So that already show, in our lab already extremely promising, right? Okay, this also as in the operating condition, one sun condition is not just I have this thing tested, in those accelerated testing conditions. In the operation, okay, then you can see the one sun is shining light, then you start to generate charge all transporting and operating, and as that thing, you try to do accelerated testing. I think company will do much better job than a few of graduate students, right? So this just show you have some roadmap, okay? Otherwise, I quit my job today.
And also regarding lead capturing, okay, you mentioned about you will keep 80%, right? Is that good enough?
Not enough, okay? So you will have something to capture 100%, right? Okay, so that's a paper we just submit to Joe, okay? And then, it's just outside you have some encapsulant. Very simply, you can code it, okay? So you can combine extracting layer, attracted 80%, then the rest of the 20% was saying anything you want to do. That already in that paper.
But then the temperature will get up again.
Huh?
The temperature will get up again because you would sort of keep the heat inside your cell.
There's no difference in any encapsulated device, right? The temperature will be operating, okay, whatever the transport. But since it's not because of a heat generation, a lot of generation in our device. It's mostly external device. For example, I have a solar cell. I need to survive in Saudi Arabia or survive in Seattle. Okay, that's a totally different environment, right? Saudi Arabia maybe 50 degrees C was 55 degrees C during the daytime, but in Seattle maybe 15 degrees C. But then a lot of moisture, right? So it's a very different environment. So you need just to develop the materials and also devices to address all those different environments. Okay, you cannot just say I have a device can only fit for a certain environment, right? So with a proper encapsulation, that can be addressed.
Okay, thank you.
So that's from your son, right? Good job, Dad. Okay. Number 5, thanks for your exciting talk. What is lifetime of PVSC? From Kong Hin.
Okay, PVSC. Okay, so perovskite solar cell right now. Okay, and people are talking about especially recently, I think demonstrate perovskite solar cell can be more than I think 100,000 hours. Okay.
Okay. So number 6, how is reliability test of the printed organic solar cell? Can it fulfill this IEC data as required for the standard PV product in the market? From Eric Leung.
Okay, so today in my talk, I just mainly discuss about lab research results. Okay, it's not in the development stage. Okay, because whoever the collaborator we have from the company and also in the development stage. Okay, then I think that will be the issue. Okay, you need to really find a way to, just like we are trying to address for perovskite solar cell. Okay, so it's no different. You have to find a way to be stable, try to capture all the lead. All those issues you need to address.
Yeah. Maybe we can continue. What's your new direction after the V6 Gatlin from Li Gaoping?
So Y6 already give you about say 15.7%. Okay, but then from that type of the skeleton, and then you optimize some of the functional group or different things that can already give you around maybe 19% or 20% range. So if you continue to do that, okay, then I think right, you maybe need to have because the reason why Y6 is very good because they have very nice conjugate backbone, and then the charge can exciton can delocalize along those backbone. Okay, and then to give you a relatively longer lifetime. So how do you come up with molecular structure allow you to achieve that, but then still have enough solubility and also processability for you to process? I think that'll be some optimization work. Okay, from molecular design point of view. Yeah.
Okay. Any question in the audience? Will, are you? No. You promised to give one, right? And then we have question. Have you tried the outdoor application? Follow-up question from Eric Liang.
As
Yes,
I just
sir.
explained right now, we just today I mainly talk about our research results. Okay, it's not this is not in the development stage yet. Okay, so this will answer your question. Yeah.
Yeah. So the organic solar cells seem to be safer but more complex structure, while the perovskite solar cells seem to be simpler in structure but more risky in safety and contaminate from the interaction with the environment. Do this system will have better at different conditions from long lai chi?
Okay, so through the years, right, and I think people also try to come up with a very different way to create innovative perovskite solar cell. So instead of a 3D perovskite, okay, now if you engineer, okay, larger size ammonium salt or different size cation, then you can make a 2D, 3D hybrid system. And 2D just form very nice coating on top of your 3D system in that. Okay, so that result, you can prevent all the moisture, prevent all the stimulant, okay, from interacting with your perovskite. So this, just like perovskite, only been studied for about 10 years, right? And just I show you from the beginning, by tuning the different size of different kind of cation, you can make it 3D, 2D, 1D, all the different kind of material. Depends on your imagination and also intuition. Yeah.
Mm-hmm. Yes, Michael.
Yeah, thank you, Alex, for a wonderful talk and very exciting. I'm not in the area, but so I have two questions. You mentioned about these conversion efficiency. There's a theoretical limit. Now you almost reached the limit, and many other people is working towards that, right? So once the limit has been reached, what's the next step?
So okay.
So this is my
that's a good
question. Yeah.
So the question is, if you have one layer of the either perovskite or OPV, right? You absorb certain region of light, right? Okay, and just like what I show you in the tandem cell, okay, and then if you look at in here, right? This is a region silicon absorb. Okay, now on top of that, I put in a perovskite in the large gap perovskite absorb this region of light, right? Okay, because perovskite only absorbs this region of light. Silicon only absorbs this region of light. So I can make a tandem cell. What all those are very expensive solar cell in the space station, right? On those solar cell, they are making the tandem is maybe triple tandem, the multiple layers structure in order to absorb any light you can generate. So that can go up to 40-something%. Okay. So for single junction, it's about you can get a limit. It's about 29% or something like that. But then if you start to really put a tandem, this already close to 30%, right? So if you make it, adjust this, make it more efficient, okay, then you can potentially go to 35% or 40%, okay, right? So this is continue. You can you imagine, right? So right now, okay, in all the panel you see outside, right? It's about 18%, okay, or 20%, right? But then if I can get it to 30%, 40%, right? Then I can actually, make it much more efficient. But the reason why space station use those are very efficient one because it's very expensive to make, right? But if I can use a printable solar cell to make it much cheaper, right? Those also address those issues.
Now, I have just another question about the application, the commercialization part of this technology. Now you use OLED in the beginning.
Yeah.
OLED technology was available like more than 20 years ago.
No.
Is it?
It's been studied. Okay?
Yeah. Okay, but it takes the industry that long to replace the previous technology. So now that silicon panels been implemented for many years,
So
so how long do you think it's going to take to replace that?
So this is the things. Okay, I was very encouraged by the report just coming out. Okay, from the prediction 2030. Okay, the perovskite solar cell in the different form. Okay, right? Either use as a tandem, use of a perovskite, or whatever form in that is going to also taking over. Okay. Silicon's market very significantly. Okay, I forgot it's either 30 or 60%. Okay, by 2030. Okay, so that's the prediction. Okay.
Good. So I think CTU Enterprise should invest in the project. Yeah.
So we are welcome. So yesterday we received that email. We're very excited. Okay, about this, right? So maybe we can talk about more about this. Yeah.
Oh, let me even. What is efficiency of the printable PV from Bella Wang? 11 efficiency of the.
What is the efficiency of the printable PV?
Yeah.
Okay, so printable PV. If you have a perovskite solar cell right now, you already can. I think in the module. Okay, right now is about if you have say 10 by 10. Okay, module is about 17 or 18%. Okay, right now.
Okay. Yeah, there are quite a lot of solar cell molecule system. I do wonder which one would be the final one. Okay, the application of this much molecule.
So I wish to know, right? Please just tell me which one I need to make, and then I will concentrate on that. So this is always you learn from the you learn from your past, right? Okay, and then you learn. For example, I show you a lot of a slide about the single crystal, right? You learn from how do you have those molecules that can control their packing, how can you really mimic that, okay? Then slowly you start to come up with your design can reach that, okay? Because it's, I think a lot of things related to you learn from your all the available information and also intuition. Okay, you can put all the things together in order to design suitable material. Sorry, I don't have a magic bullet to tell you if I only need to make this molecule. Okay.
I think we are approaching 12, so time is up. And we finished all the questions. So I think we have a very nice presentation, very good Q&A section. So I present a diamond to you. A big diamond, looks like it.
Very good.
So thanks, Professor Allison.
Yeah, thank you very much. Thank you.